All right, in section 8.8, we're going to turn our attention to reactions of hydrocarbons. And it turns out that if you have an alkane, it turns out that alkanes are actually quite unreactive. So alkanes least reactive of all the organic compounds. In general, excuse me, alkanes don't react with strong acids like sulfuric acid or hydrochloric acid. They don't react with strong bases like sodium hydroxide, potassium hydroxide, lithium hydroxide, oxidizing agents like potassium dichromate, or reducing agents like sodium metal. So not very reactive. However, alkanes do, as a matter of fact, they do undergo reactions with halogens like chlorine, Cl2, or bromine, Br2. But we're not going to worry about those for our purposes. You can also burn an alkane, and if you think about it, propane and butane, those are hydrocarbons, they're alkanes, and we burn them in our everyday lives. Propane in a barbecue tank, and butane would be in a butane lighter. But that was previously discussed back in chapter 4. And you probably remember that when you combine a hydrocarbon, CxHy, with oxygen, you end up making carbon dioxide and water. And again, that is combustion. Okay, that's burning a hydrocarbon. But what we're going to be interested in this chapter is going to be reactions of alkenes, and to some extent the reactions of alkynes, because of the presence of carbon-carbon double bonds or triple bonds. It actually makes alkenes and alkynes more reactive than an alkane. And so, because both alkenes and alkynes rely on the reactivity of a multiple bond, their reactions are in fact going to be quite similar. So again, we're going to concentrate on the reactions of alkenes and alkynes. Why? Because they contain double and triple bonds and they're more reactive than alkanes. All right, our first alkene reaction is going to be what we call alkene addition. So it's where we take our carbon-carbon double bond and we're going to add some kind of molecule to it. Okay, so here they have AB, and we'll take a look at some examples of what those could be. And so what's going to happen in a nutshell is you're going to end up breaking or removing the double bond. I'll just scribble it out like this, okay? And then you're going to end up adding the A and the B here, and you can see that that's in the products. I'm making a bit of a mess here. But anyhow, so that's what we do is we break that double bond, and then we end up adding A to the first carbon, and then we add B to the second carbon like this. And again, we call this an addition reaction. We're adding AB across that double bond. And so we have to have an alkene, and then we have our AB molecule. So let's take a look at what some of the AB molecules could be. All right, and one of the possibilities for an AB molecule would be hydrogen, right? So you have A and B like this, so why not HH, right? The A and the B are identical in hydrogen. And when you add hydrogen across a double bond, we call that hydrogenation. And so it says here that a reaction in which the addition of hydrogen takes place, a precious metal catalyst, either palladium, platinum, or nickel, is typically needed to make the reaction work. And if you remember, a catalyst just speeds up a reaction by lowering what's referred to as an activation energy. So here's a generic example. Right here, we have our alkene. We have our hydrogen. Now keep in mind this is H2, right? Hydrogen is a diatomic element, meaning when it's found in its pure form in nature, it exists as H2. And if it helps you, you can write out H2 like this. And so on one carbon, we're going to add one hydrogen. And on the second carbon from that double bond, we're going to add the second hydrogen. And so we go from an alkene to an alkane. And you can see a very specific example at the bottom shown the hydrogenation of 2-butene. We have 2-butene, we have two carbons involved in our carbon-carbon double bond. We add a hydrogen to one of those carbons, we add a hydrogen to the other, and we go from an alkene, butene, to an alkane, butane. So that is hydrogenation. Now, it turns out that hydrogenation is used to take vegetable oils like soybean oil or cottonseed oil and take them from being highly unsaturated to more saturated. And that's how margarine is made. So if you've ever had margarine before, what they do is they hydrogenate. And if you're asking, do they literally add hydrogen to an organic molecule? The answer is yes. That's how margarine is made. But when we start out with a vegetable oil, like I said, they have a very high degree of unsaturation, which means lots of double bonds. And so instead of saying a high degree of unsaturation, we say polyunsaturated. And so that's a term we just apply to any molecule that has many, many double bonds in it. And so what happens is when you hydrogenate a polyunsaturated compound, it reduces or converts those double bonds into single bonds, and then it increases the melting point. So you can take vegetable oil, as you add hydrogen to it, the melting point gets higher and higher and higher, and it goes from, right? It's going to go from the liquid phase to the solid phase. So you have your vegetable oil. I'll just put V oil over here, which is a liquid. You add hydrogen to it with palladium, platinum, or nickel. I'll just choose platinum, and you get a solid. And that is how you make your margarine, like that. Now, this isn't part of the class, but I'll just point this out to you that during this hydrogenation process, the double bonds in naturally occurring vegetable oils are actually cis bonds. And sometimes during the hydrogenation process, the cis bonds will get converted into trans bonds, which is called isomerization. And that's where trans fats come from. They come from hydrogenation of polyunsaturated fats. And so trans fats are made by humans. They're not natural, and they have been linked to heart disease. All right, you can also see that hydrogenation is important for the synthesis of this compound here, which is called L-DOPA, which is a drug that's given to people that have Parkinson's disease. Okay. Now, we're not going to go over the synthesis of L-DOPA. We're going to take a look at a couple of examples right down here. And so these questions just ask to write the structural formula for each product of the following hydrogenation. So we can see in the first compound, we have our carbon with our double bond here. This carbon has the double bond. And so we're going to add a hydrogen across each one of those. And when we do that, we get rid of the double bond. So we're going to draw our six-membered ring, and we're going to add one hydrogen here and one hydrogen here. Now, if you're astute, and I know you are, okay, you know that there was already a hydrogen here and here. And so that means that both of these carbons now have four single bonds. And so if you had written the structure just like this, okay, that would still be the correct answer, okay? This molecule is called cyclohexene, and this molecule is cyclohexane. All right, let's take a look at the next one. We have, what would this be? 2-methyl propene is what you would call this compound. This carbon is part of the double bond. This carbon is part of the double bond. And so we're going to add a hydrogen to each one of those. So now we have CH3, CH, and we get another CH3 down here. And we're going to have a CH3 down here. So we go from an alkene to an alkane. All right, there you go. Another thing I'll mention, instead of me just saying CH3 every time and all this stuff, you should learn a little bit of the vernacular since you're studying organic chemistry. When you see a CH3, we call this a methyl group, okay? And we saw this on a previous video. But a CH2 is actually not referred to. So if you're talking about a CH2, it's not a CH2. It actually has a name. It's called a methylene, okay? And if you have a CH by itself, like this, okay, that has a name too. It's called a, oops, it's called a methine, I-N-E, a methine. So methyl, methylene, and methine. All right, next we're going to take a look at hydration. I bet you can guess what that means, right? Hydration is going to be the addition of water, right? If you hydrate yourself, you're adding water, right? You hydrate an organic molecule, you're adding water. Now it says here, in the absence of a catalyst, water doesn't react with an alkene. However, if you use a catalyst like sulfuric acid, and you remember the formula of sulfuric acid, it's shown here on the slide, it's H2SO4. That's going to speed up the reaction so you can add water across your double bond. So if we take a look at the example of hydration that they've shown here, and there's a generic example shown right here. Okay. Now, if you're looking at this and saying, I thought water was H2O, yes, it is, right? But we could also write the Lewis structure of water like this. And they're just saying, okay, well, what if we just condense one bond like this? And so that way, we can think about this as being kind of like A and B, right? This is our A portion of the molecule. This is our B portion of the molecule. And so on the first carbon, we're going to add the A portion, the hydrogen. And on the other carbon that was formerly part of the double bond, we're going to put the OH group. And so now you can see that we've gone from an alkene to an alcohol. All right, and you see a very specific example shown down here. This is 2-butene, and when we take 2-butene and we hydrate it, right, this carbon is going to have something added to it, the hydrogen in this case, and this carbon will have the hydroxyl added to it. So again, we go from an alkene to an alcohol like that when we do a hydration reaction. Now you probably noticed that the alkenes in the previous examples were all symmetric, meaning they were the carbon-carbon double bond had the same number of hydrogens on both carbons. But what if we have a molecule like propene that's shown down here in this example? Okay. If I zoom in on this molecule, you can see the two carbons aren't identical, right? This one has one hydrogen attached to it. This one has two hydrogens attached to it. So the question is, where does the hydrogen go? Does it go on this carbon or does it go on this carbon? And for that, we're going to answer that, we're going to employ what's called Markovnikov's rule. So it says here, in the addition of water, oftentimes you can get two possible products. And you can see both products are shown here. The first one is where the OH group is on the yellow carbon, and this one is where it's on the carbon that I have highlighted in green. However, we only get the 2-propanol as a product, and that is because of Markovnikov's rule. And Markovnikov's rule states that in the addition of HX to an alkene, the hydrogen becomes attached to the carbon that is already bonded to more hydrogens. So if we look at these two carbons, the one that I have highlighted in yellow, the one I have highlighted in green, which one of those carbons is attached to more hydrogens? The carbon in yellow is attached to one hydrogen. The carbon in green is attached to two hydrogens. What is a bigger number, one or two? The answer is two is a bigger number than one. And so this hydrogen is going to get attached to the carbon that had more hydrogens. And the OH group is going to get attached to the carbon that had less hydrogens. And that is how we decide what our product is. And that is Markovnikov's rule, a rule you must memorize. So according to Markovnikov's rule, when a molecule of water adds to an alkene, the hydrogen becomes attached to the double bonded carbon that is already bonded to more hydrogens. In other words, the hydrogens go where the hydrogens are. Sometimes my students will say the rich get richer. The carbon that is richer in hydrogens takes on the new hydrogen. So again, if we look at propene, we look at the two carbons in the double bond. The carbon that I have highlighted in yellow doesn't have as many hydrogens as the one that I have highlighted in green. And so the hydrogen goes where the hydrogens are, or the rich get richer. We would add our hydrogen to this carbon, and therefore the hydroxyl, the OH group, would be attached to the carbon in yellow. All right, hydration is one of the steps of the citric acid cycle. Draw structural formulas for the major organic product of each of the following reactions. Well, if we look at the first example, if you look at this carbon that I have highlighted in green and this one I have highlighted in yellow, they both have one hydrogen attached, okay? Right, because carbon always has 4 bonds. We have our water and we have our sulfuric acid catalyst. So we're going to have a hydration reaction occurring, but there's no Markovnikov to worry about because both carbons are equally rich in hydrogens. And so we're going to end up with the hydrogen on one carbon and the hydroxyl or the OH group on the other. Now, what I've drawn there is the same thing as if I just did something like that. Okay? Now, in the second example, we will have to employ Markovnikov's rule because if we look at the double bond, this carbon has one hydrogen attached to it, but this carbon, which is also part of the double bond, where's my highlighter? This carbon has 0 hydrogens to it, 0 H's. So what is a bigger number, 1 or 0? The answer is 1. And so the hydrogen is going to be attached to the yellow carbon, and the OH group is going to be attached to the green carbon. So we're going to put in here CH3, CH2, C, and then this one is going to have the OH group. There's my methyl and my other methyl here, like that. There you go. So again, this is going to be the only product. And for the second one, again, it is the Markovnikov product. Okay, is what we call that, the Markovnikov product. Now, we would be remiss to study organic chemistry without studying polymers because polymers are organic molecules. We might not think of them as being organic molecules, but they are because they're made out of carbon. And there are many polymers that we find, everywhere in our lives, whether it's, Kevlar or polyester or nylon or polyethylene terephthalate. There are many polymers out there. And so if you think about the word polymerization, what does that sound like to you? Well, polymerization is nothing more than the reaction that makes a polymer. So if you take something that isn't a polymer and you convert it into a polymer, that is polymerization. And polymers like plastics or even like I said before, Kevlar or Teflon, those kinds of things, they're just very big molecules that are made up of units that repeat over and over and over. But if we break a polymer down into its simplest possible repeating unit, like the part that is repeated over and over and over, we call that a monomer. And then an addition polymer is a polymer formed by linking together many alkene molecules through addition reactions. And so you can see here to make polyethylene, what they do is they take ethylene and many molecules of ethylene. That's what the N stands for. It's just a whole bunch of them. We put them together with heat and pressure and some catalysts, and we end up with polyethylene. So you notice that we went from an alkene to destroying the double bond, right? Okay. We break that double bond and then we connect more units of the ethylene at each end. That's what these parentheses mean here. It means that you have another unit of CH2, CH2, and then another unit of CH2, CH2, right? But it's the same thing that gets repeated over and over. Two methylene groups, right? Two methylene groups, et cetera, et cetera. And so this table shows you some common addition polymers and the structure of the monomer and the polymer. So we've got polyethylene, okay, which is used in things like plastic bags. Then we have polypropylene. It says here carpet fibers, pipes, bottles, artificial turf. Artificial turf is a good example, but I'd also say ropes. There's a lot of ropes that are made of polypropylene. Next, we have polyvinyl chloride or PVC. You guys know about PVC water pipes, I'm sure. Next one is Teflon, polytetrafluoroethylene. Teflon is found in nonstick cooking pans, right? The next one is polymethyl acrylate, which is found in things like plexiglass, okay? After that, we have polyvinyl acetate. So polyvinyl acetate is used in adhesives and paint. Okay. Then we have polyacrylonitrile, which sometimes goes by these trade names like Orlon. And now those are found in things like certain kind of clothing fiber or clothing fabrics rather, and also carpets. And then the last one, I'm sure you've all heard of polystyrene before. That's the initial styrofoam was just a polymer of polystyrene. So of course that's found in things like coolers and cups, that kind of stuff, insulation. All right, so some polymers. I'd also add, if you want to look it up, Kevlar. Kevlar is a polymer. Nylon would be another. There's different types of nylons, but nylon is also a polymer that you would find in your everyday life. Also, there's polycarbonates, like bulletproof glass is made out of a polymer, just like Kevlar, which is also bulletproof to some extent. All right, the synthesis of specialty polymers for medical devices like vascular grafts is a very active area of science. Draw the structural formula of the portion of the polypropylene containing four repeating units of the monomer propylene. So again, if we go from our monomer, all right, this is our monomer, and we want to draw our polymer, all we're going to do is we're just going to remove the double bond, okay? Then we're going to link it to another one. And again, we just remove the double bond. So that's two. It asked for four. And we do another one. And then we do another one. And that's it. That's four repeating units. So I'll say that goes to something. And this goes to something. And I'll just put N here, meaning it just repeats over and over and over.